because you can't really have a tangent line and a corner. If it was rounded off there, then it would be a real nice, smooth little transition from negative to positive, wouldn't it? But at a corner, it's like negative, 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 and then you blink your eyes and you're positive. Make sense? Okay, what about from here to here? The derivative is always negative and it stays the same value the whole time, and it looks like, again, down 2 over 1, the slope of that line is negative 2. So now we're back here again, down like this, negative 2. And then I'm going to leave that as open and leave that as open and leave that as open. And then what happens when we get to here? Blink your eyes, back to positive 2, and we're up here and it goes like that the rest of the way. The red graph is the graph of the derivative. Very awkward looking derivative, right? Does this make sense? The reason we don't connect these, or like, what do you mean? Oh, like a straight line? Is because then it wouldn't be a function. Exactly, it would fail the vertical line test. I think that's sufficient. I think we're ready to move on into the section.
How would you write that?
How would I write what?
Like the derivative.
I would draw it. That's all we're asking ourselves to do is draw it. Now, I will give you a function later and then ask you to find its derivative. Algebraically. This is just, all we're trying to do right now is try and understand what the derivative means visually. Here's a good challenge problem. Let's see how you do with this. See that? You ready? You fry your brains here. That's the derivative. Draw me the original function. So now you're going backwards. I'm giving you the derivative and you're trying to come up with the function. So what are some important points on this derivative? Where it's above and below the x-axis, right? So like we know over here, right, the derivative is negative, which means my original function is doing what over here? It's going down, right? And then between here and here, my derivative is positive, which means my original function is going up. And then right here to here, my derivative is negative, which means my original function is going down. And then over here, my derivative is positive, which means my function is going up, right? Now, what about these points? These are important points right there. Where my derivative is 0 is where my original function flattens out, right? Right? Okay, let's try and draw this. I'm just going to start somewhere. I'm going to just go for it. There, I'm just putting a point, because I don't really know anything about the function other than whether or not it's like going up or down. That's all I really know. So I know it's going, until I get to this point, as I draw it, it's coming down, right? Because the derivative is negative. So it's coming down. And when I get to this point, what happens to the derivative? It comes to 0, right? So it goes like that. Okay, see my derivative is negative, 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 and then it goes to here, it gets 0. And then once I get past this point, what? Positive, right? Derivative, which means it's got to start going back up, right? And then when I get to here, my derivative has got to be 0 again, right? So it's got to flatten out again like that. Do y'all kind of see that? And then what about between here and here? It's going down. The original function is going down. But it's got to go down and then get back to 0. So it's got to go down and then it's got to get back to 0, right? Like flat. And then once I get past this point, it's got to start going back up again. So that would qualify as an F. Now there are a bunch of other answers that would work. You know, you might have drawn that entire graph down here. You might have drawn your graph more like this. Oh, well, sorry. Yeah, you could have done something like that. I mean, but there's certain characteristics that it has to have. Yes?
Is that a negative sign?
Is that a negative what?
Sign function?
No, this is just an arbitrary, I'm just,
But it kind of looks like
which one?
the original one looks like a
This one?
sign. Well, that's a cosine. That looks like a cosine.
Well, I'd argue that looks more like a negative sign than those look, because they're not, these aren't the same heights. So with sine functions and cosine, you got to have the same top and bottom. All right, let's get into the notes. Let's get back into the notes. Y'all doing all right? Happy Valentine's Day. Yep, I'm using red a little more up here today. I can feel the love in the air. All right, now, we have now established that if we're given a curve, y equals f of x, then we have this new idea of the derivative of the function. But instead of saying derivative at at a, we're saying derivative at x, and that's a new function, right? And this is now the new notation you may see anytime someone wants you to take a derivative. Okay, so if I give you a function y equals f of x, if you see me write find f prime of x, that means I want you to find the derivative, right? If I write just y prime, I mean find the derivative. If I write dy over dx, that means go find the derivative. If I write df over dx, that means find the derivative. If I write d over dx and then the function, that means go find the derivative. Capital D of the function, go find the derivative. Capital D subscript x, find the derivative.
Is there any difference between any of these?
No, these are all exactly the same thing.
Why are there so many?
Okay, so in a different calculus class, you deal with functions that have more than one input. So like you might be dealing with a function where you say y is equal to some function of x, r, s, and t. In other words, I have something that takes in numbers, x, r, s, and t, takes all four numbers in and spits out an answer. Okay? And so we can look at the derivative of this in a Cal 3 class. But when you take the derivative of this, if you just write f prime, or if you were to write like y prime, what you have to know in that calculus class is which variable are you treating as your true variable in the problem. And so you'd want to use a notation like this because it allows you to talk about what variable it is. Okay? And now this notation, the reason why we use that notation is because there were two people who came up with calculus. There's Isaac Newton and Leibniz. And when they created calculus out of their own brains, right, they used different notation because there was no notation. No one had notation for derivatives yet because they were making it up, right? So Leibniz used this notation while Newton used the primes. And that's just the way they chose to do it. So that's what I say right here. The dy dx is called Leibniz notation, named after the other father of calculus, Gottfried. All right. We will use both notations. I mean, the notations we're going to use the most are these three. Those are the ones you're going to see the most here. All right. But just be aware that if something pops up in some other physics class or something like that, and they have like, d dx of something, it's the same thing. Just take the derivative. Find the derivative. All right. Now, since the derivative of a function gives us a new function, we have this new definition saying that if someone gives us a function f, we will say that it is differentiable at some point a if the derivative exists. So you have to remember, the derivative comes from a limit, doesn't it? The whole idea of a derivative is we have to take a limit. And sometimes limits don't exist. We did that, we've seen that. Limits don't exist sometimes. If the limit exists, then we will say it's differentiable at that point. If the function is differentiable on an entire interval, at every point inside the interval, then we say it's differentiable on the open interval. So there's a difference between being differentiable at a point versus an interval. Interval is a very strong condition because it means at every single point that limit exists. So we have some nice theorems. This one right here says that if you can take, this basically is saying if you can take the derivative of a function at a point, if it's possible, if that limit exists, then you're guaranteed that the function has to be continuous there. Do you remember what continuity meant?
Yes.
You're like picking up, like drawing without picking up your pencil? Yes. This is saying, look, if you pick a point on a graph and you tell me that I can take the derivative there, then I promise you that the function is coming in from both sides to that point. Okay, it's guaranteed. This theorem is important, but it's not important for this class, all right? It's just, I need to state it. The thing, though, that I do have to point out is that you have to be careful with the way this is stated. It's saying if the derivative exists at a point, then you're guaranteed you must be a continuous function. It is not saying it the other way around. So I like to give students an example. This is kind of like an exercise in logic. So if I write this on the board, if you're a Texan, and what I mean by Texan is that you live within the boundaries of Texas. Okay, we're not going to get into any sort of debate about, where, whether or not legal, just if you live in the boundary of Texas, we're going to call you Texan. If you're a Texan, then would you agree that you are a U.S. resident? You live within the U.S. boundaries. At least now, right? Texas hasn't seceded yet. But for right now, if you're from Texas, you're basically living in the United States. We all agree? Can you flip that over? Can you change the order of that? If you're from the U.S., if you're within the U.S. boundary, then can you say that you are in Texas? No, right? So the order in which we state things, right? You could be in California, right? You're in the U.S. That doesn't mean you're in Texas. But if you're in Texas, you have to be in the U.S. This is saying if you're differentiable, you have to be continuous. This does not mean that if you're continuous, you have to be differentiable. I'm going to give you an example right now of some functions that are continuous that are not differentiable. So when do functions fail to be differentiable? When do we actually have problems with the slopes of tangent lines? Like when does it happen that we could have an issue? And there are in this class 3 things that we will deal with. The first is if you ever have a corner or a cusp at a point, then your function's not going to be differentiable. If you ever have a jump in the graph, you're not going to be differentiable. Or if you ever have a vertical tangent line, you're not going to be differentiable there. And I'm going to show you a picture of each one. So look at this one right here. This is like that one, that W function I showed you a second ago, right? And we drew the derivative and it like went and all of a sudden it jumped up and we said, what happens at that jump, right? I said, leave it as open circles for now. Well, if we look at the slope of the tangent line, right, there's our slope of our tangent line. If I start to graph it, right, here I'm graphing, there's the derivative. Does it make sense that that derivative is staying constant?
Yes.
Okay, and then once I get past this corner, it's going to jump down and be negative. But see, at this jump, so at 0, that function fails to be differentiable because we have a corner, right? We have a corner. Anytime you have a corner, it is not differentiable at the corner. Is that all right?
Did you just say that anytime there's a break, it's not differential?
That's the next one. This is not a break. Oh, a break in the derivative.
Yeah, as in like break or not.
Okay, I thought you were referring to the original function. Yeah, if the derivative has a break in it, then your original function had a problem with the differentiability. Okay, so not differentiable at a corner. Just FYI, I said in the note here a cusp. The difference between a corner and a cusp is that a cusp looks like this. Okay, that's a cusp. A corner is like, an upside down V, or it could be this way also. So you would be not differentiable at those points. But it had to be like jagged wave. If it's rounded, does the derivative exist here? Yes. Because your derivative is nice and smooth. It comes in, derivative is positive, 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 but getting closer to 0, gets to 0, and then becomes negative. So there's a nice smooth transition between the positive to negative. Where here it was like positive, 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 and all of a sudden it's like shaking a child. ugh, and all of a sudden you're like negative, right? No?
Say you're trying to get that.
That you shook the derivative and hurt it by, making it switch from positive to negative.
If we were to microscope, please.
Maybe that wasn't a good analogy.
It's probably how shaking babies.
Yeah, maybe. I don't know why I'm talking about shaking babies here. Okay, let's keep going. Not a good sign. Not a good sign.
All I know is that to save a drowning baby, you take it off.
All right, what about this? This graph right here, here's a function, and we have a problem with the derivative because we have a jump in the graph. In the original function, we have a jump. So if we have a corner, we know we have a problem. If we have a jump in the graph, we have a problem. And just take a look at the derivative. It's going to be positive. As I come in, it's positive, right? Then all of a sudden, again, boom, it jumps over, right? And becomes a different slope. Do y'all see that? My graph is, you can't see the derivative. There it is. There's the derivative down there. It's negative, see? So your derivative, again, violently goes from positive to negative. Not good. I've never used that analogy in this class. I think I'm going to start using that from now on. All right. What about this one? There is not a corner, there's not a cusp, and there's not a break or jump in our graph, but we still have a problem. And this is the third type. We have what we call a vertical tangent line. So watch the tangent line here. Slope is positive, right? Positive, positive, positive coming in. And then as I start to get close to this, keep an eye on this number here. This is the slope of the tangent line. As I start to move in here, getting closer to 0, do you see that that tangent line is wanting to get more and more vertical? And do you see the value of the derivative? Right now, what's the value of the derivative? 21, very steep. I'm going to keep going, closer and closer and closer. Do y'all see it's getting steeper? 74, 97, 154. I'm just like inching my way into that, to 0. And that thing's trying to go straight up. Yes?
Are there two derivatives, or you just the other lines just to show like the verticality of it?
Oh, this one right here versus that one?
Yeah.
This right here is the tangent line. This one is the slope of that tangent line, right? So this green one is representing how pitched this one is. So they are different. They're different things. Okay, I think we keep going in there. I'm about to be done. It's growing 240, 283 something, 4 something, 7 something. Uh-oh, boom, look at that. That's when I hit the mother lode right there. I got real close. Look how steep that line is. 1 with like 10 zeros after it. That's the steepness of that line. So it's wanting to become infinite, right? So that means at 0, you can't have a derivative. Because at 0, your line will be vertical. And slopes of vertical lines are undefined. So recap. Places a function will fail to be differentiable. Corners or cusps. Breaks in the graph. Anytime your graph goes and starts to create a vertical tangent line. That's what was happening with that square root function. Remember we were looking at the square root function earlier like this? And we were trying to move that tangent line like that? It was trying to become vertical. And so our derivative would not have been defined at 0. Oh, a famous function. For the longest time, mathematicians pondered that theorem that I just had up there, the one that I did with the Texans thing. It said, if you're differentiable, then you have to be continuous, right? But it doesn't work the other way around. And so mathematicians were like, I wonder if there's a function that's continuous everywhere. That means you can draw it without picking up your pencil. But you can't take the derivative anywhere. Understand the question? Is it possible to come up with a function that you can draw without picking up your pencil, but nowhere can you take the derivative? You always have a problem everywhere on the function.
If it was a line, horizontal line, right?
Then it wouldn't be a function, right? So it has to be a function that you can draw without picking up your pencil, but you can't take the derivative anywhere. And they searched for it for a long time, and then finally someone found one that does it, and it's called the Weierstrass function. It's really a cool function. Remember, we have, anywhere you have a corner, right? You have a problem. So imagine that I come up with a function that does this. Do you agree that that function would not be differentiable, at least at these points? But in between those points, it would be okay, wouldn't it? So that's not a good function. But imagine that the function I created, if you were to take that and zoom in on it and take a look at that piece. So zooming in on that little piece, what if I told you that that piece that kind of looks like a line far away is actually jagged like this? So this little piece right here has little saw teeth, kind of, right? Then it wouldn't be differentiable at each of those corners, right? And then what if each of those little pieces, if you zoomed in on it, had little saw teeth? And you could zoom and zoom and zoom forever, and you'd always have saw teeth. Then you would have the function we're looking for. And this is actually it. That's the function. Now I know that looks crazy, but let me kind of zoom in on this so you can see what I'm talking about. Okay, so it kind of looks like, do you see how it looks like a bunch of like little jaggeds? Now I'm not showing you the whole function. I have to actually add some more pieces to it. Too many pieces. The jaggedness. Still no good. I don't know if this is going to work. Not a very good picture. But I think this is a better idea. You have a saw blade, and then within each of the teeth of the blade, you have another saw blade, and each tooth there has a saw blade. I'll look it up real quick on Google, just so you can. Would y'all like to see what the function looks like?
Yes.
The Weierstrass function. There we go. Oh, okay, that's a pretty good picture of it. Do y'all see it right there? Yeah. Where is it? Oh, there it is. There it is. This is it. It is an infinite sum of cosine functions. Now, we haven't dealt with that. Okay, we've never dealt with the idea of defining a function to be an infinite sum of functions. Take Cal 2, and you can deal with that. We call those infinite series. So it's actually just a bunch of cosines added up, and I don't know what's going on there. Okay, so this is showing it. This is showing it. Imagine this is a cosine followed by another cosine, cosine, cosine. If you start with just the first few cosine functions, it looks like that. But as you add more, it starts to get more jagged. And as you go out through the sum, it starts to create all the little saw teeth. Okay. So yes, there is a function out there that you can draw without picking up your pencil, but you cannot take the derivative anywhere. That's more of an FYI. You won't ever be tested on that. Do y'all agree that you could draw it though? Like you've got this pen that does some weird sort of vibration the whole time you're drawing, right? It's always making jagged little.
So basically, I forget the name of the device that they use to measure earthquakes.
I guess so. I don't know. I mean, yes, it's vibrating, but it's more theoretical than it is anything else. Okay, because you could never make an instrument that does that. All right, higher order derivatives. Well, since the derivative of a function usually gives you a new function, right? Then why not take the derivative of that function? And then ask the question, what the hell would it mean, right? We will answer that. But we are going to do higher order derivatives. That means taking the derivative repeatedly of a function. And so we need some new notation. If we already agreed that the derivative of a function is f prime of x, we will now call that the first derivative. And if we want to do the derivative again, so take the answer and then take the derivative again, then we'll use f double prime, 2 little prime marks, and that means you take the derivative, and then after you're done with that, you take the derivative again, and that's called the second derivative. And as you would expect, 3 prime marks means the third derivative. Now, once we get past the third derivative, we start to use a different notation. Instead of using prime marks, we put the number of the derivative here in parentheses. And that means take the fourth derivative, fifth derivative, and so on. Don't confuse that with this. So watch. Let me give you a function. We all miss that function, don't we? Life was much better back then. Okay? So if I say this, I want you to take the first derivative, right? If I do, that's a 4. If I say that, then I want you to take the derivative. After you get that answer, take the derivative again. After you get that answer, take derivative again. After you get that answer, take derivative again. 4 derivatives successively. Don't confuse that with this. What does that mean? Take that, and no derivatives. Take that, raise it to the 4th power. This means take x squared and raise it to the 4th power. So there's a very important thing here with those parentheses around the number. That's talking derivatives. No parentheses around the number, that's talking just algebra, raising things to powers. And so on and so forth. Now, I like this notation, but Leibniz was also one of the fathers of calculus, so how would you do higher order derivatives with his notation? And it looks pretty bad, but I don't know, maybe it'll make sense to you. So if the first derivative was dy over dx, then does it make sense that we would do d squared y over dx squared? Whoa, that's weird. That's not a typo. D squared y over dx squared. D cubed y over dx cubed. D to the 4th y over dx to the 4th. Why the offset numbers like that? Is that just to make your life hell or what? What do you mean?
Like if you did d squared over d squared, it'd just be 1.
Let me try that. What if I did dy squared over dx squared like that? What if I didn't offset that too? These wouldn't quite cancel, but students might think that this means dy over dx squared. That's what they may think that means. And this means what? What does this mean? Take the derivative, right? Take the first derivative, and then we get that answer, square it. And that's not what we mean. We mean take the first derivative and then take the derivative of that. So in order to eliminate that confusion, we offset the numbers so that we don't think that, okay? Fifth derivative and so on and so forth. All right, some nice other consequences. Do you remember how I said that if we have an object moving in a straight line, if an object moves in a straight line, then the derivative gives you the instantaneous velocity, right? That's what we said?
Yeah.
Okay. Then the second derivative gives us something else. It gives us, so if we take the derivative again, it gives us the acceleration function. All right? Gives us the acceleration function. This is, I think this is pretty worth noting. Someone give me an example of a speed. Like if you were to be talking to someone about speed, how would you say, like the speed you're going in your car, what would you say? Miles per hour, right? Meters per second, right? Per, no, so a light year doesn't use a per. What is a light year? Distance light travels in 1 year, right? So you've got distance over time there, right? So miles per hour, feet per second, whatever, right? That's a unit of speed. Keep that in mind. Anyone know how we would say acceleration? So physics people, like what are some things you've heard with acceleration? Acceleration of gravity.
Difference of the speed.
Yeah, but what, like a unit, like, do y'all know the acceleration of gravity? Have you heard it? Negative 9.8 meters per second. Have you all ever heard that before? So the unit for acceleration is meter per second per second. But you could also go feet per hour, or miles per minute. Okay, speedometer, miles per hour. Acceleration, miles per hour. Try and explain what's going on here. Let's say that you have time here and you have distance here. And you have some function, right? The slope of, if you pick a point here and you find the slope of that tangent line, that's the derivative, isn't it? And the derivative is rise over run. Yes? Rise over run. Rise is distance, run is time, right? So distance over time would be the slope of that, would be speed. So the derivative of this is speed. So if this is the function f, then I could graph its derivative over here. And I'm not going to get all technical about what it looks like, but I think it looks something like that. Who cares? If this is the derivative, right, then this is speed on the y-axis, and this is still time, right? So if I do speed over time, that's like, you know, what? If I take a slope of a tangent line here, right, then rise over run is speed over time, right? And that's acceleration. So you have acceleration. If we take a second derivative in time here, that would be your second derivative, whatever that looks like. So let me see here. I can try and do this with a distance. An example would be if this was miles and this was hours, then this graph just tells you how far you've gone after a certain amount of time. But this right here, this unit would be miles per hour, and this would be time. And then over here, this would be miles per hour, because all you're doing is taking, to get speed, you go miles over hours. To then get this, you do miles per hour over hours again, and that gives you your miles per hour. All I'm trying to get at is the reason why you have the relationship, when you hear acceleration, they use that time measurement is twice. It's because you're doing rise over run. You're doing the rise over run of a speed over a time. And speed already has time in it, so time appears twice, if that makes sense. All you have to know here is that the second derivative gives us acceleration, and that's going to be very useful. Y'all look like y'all are done, yeah? Well, good, because we're done with the section too. Let me take a look real quick at the, oh wait, we need to talk about the exam, right? Okay, I just want to see what the homework looks like here. For the homework for this section, you're going to have some practice looking at graphs and trying to, look at what their derivatives look like. But then you're also going to be given some functions and then asked to take the derivative, like the first problem we started class with, right? But instead of doing f prime of a, you're going to do f prime of x. So that, we might have to come back and revisit that. But in an effort to be able to talk about the exam, let's stop right here. All right, so what do you want to know about the exam? It's Tuesday, right? That it? We're good? I don't know how many questions there are because I haven't written the test. And I probably won't write it until Sunday or Monday. I have no idea how many. What it's going to be, if I tell you there's 5 problems, it's not worth me telling you that because you could have a problem that has multiple parts. So let's talk about what I expect you can do, all right? So overall, your best study guide for this is your homework and examples we did in lecture. Okay? Right? What's that?
The homework, not it's a lot of homework.
It's a lot of homework. Yep, it's a lot. Yep. I mean, it's a lot of work. So, I mean, we have to remember How many hours are you technically supposed to commit to this? I mean, realistically, this is, I think, something that loses. I've met with a lot of you. I know a lot of you work, you have commitments. But technically speaking, a full-time student, right, 12 hours, is supposed to be spending a full time doing academics, which means like a 40-hour week. So if you're only in class for 10 to 12 hours a week, those other 30 hours are supposed to be studying. And that's always the expectation in a STEM major, is that if we're here for an hour or two, if we're here for 4 hours during the week, you should be putting at least, I would say, you should be putting at least 6 to 8 hours into this outside of class every week. And if that's too much, then you might have too much on your plate. Okay, so I expect that you have done all of your homework. I did it all on video, so you have it all there for you, right? With some mistakes, little mistakes. So I will not surprise you. I'm not gonna pull some problem out of the back of the section that I never asked you to do. I'm not gonna do that, all right? But if it's something that I asked you to do for homework, I expect that you could do a problem like that with me changing up numbers a little bit maybe, but you would be able to recognize it and know what to do. Yes?
So, on 2.1, or question from 2.1, mainly the one that we did here in class, where it was that complex fraction of a long, drawn-out quotient of at least 10 plus variables all over, a plus 2.
Fair game.
Plus h, blah, blah, blah. That one big giant.
Yeah, it's fair
How
game.
many of those are you going to put on?
Well, I always make a test, I take the test, I multiply that time it took me by 5, okay? And if I can do that in so basically I need to be able to complete my own test in 20 minutes. If I can complete my own test in 20 minutes, I expect you can do it in 100 minutes. Does that seem reasonable?
Yeah.
And that's the way I do it. So I would never give you like 5 of those, right?
So
But if I give you one, you got to be able to get it because it's going to be worth a lot of points on the test, right?
One is given, but the question is you're going to use more than
I will not give you anything that I don't think that you can complete in the time that you're in here. Okay? Yes?
Which section's gonna be on that? The review one?
I would not focus at all really on the review section. So let me finish, before I get all these questions, let me finish saying what I wanted to say, okay? Which is study your homework, okay? And then also go back and review the problems that we did in lecture. Because when I make the test, I'm going to sit down, I'm going to look at the homework problems, and I'm going to start making the test. And I have actually given tests before that have been nothing but homework problems, exactly the way they came out of the book. And I've been very disappointed before because students still can't do their own homework problems. So how do you prepare for that? My recommendation, you have a friend, meet in groups, whatever it is, you have somebody go pick problems out of the sections for you, give them to you, and you don't get anything except your formula sheets, calculator, turn off the TV, turn your phone off, and see if you can get through the problems. If you're sitting there like going, I don't know what to do with this, that means you haven't done enough problems. You're not able to recognize, you're not able to, you know what I'm saying? Hold on. As far as sections are concerned, where's the sign-in sheet? There we go. So as far as sections that I would look at, I would start my reviewing at 1.3. Limits of a function. And I expect that I can give you a limit that you're going to know how to do basic limit, where you might have to do a little difference of squares, maybe factor trinomial. I also am going to challenge you to be able to show that maybe you can do a conjugate or get common denominators, right? Some sort of complex fraction. I may not give both of those to you, but I might give you one. Limits in infinity. Remember those, right? So if you have fixed over 0, you're definitely going to see something like that. You need to show me, you're coming in from one side and what happens. What happens if x goes to infinity, right? Limit x goes to infinity. You had things like infinity over infinity, and we had a bunch of different scenarios that happens with that, where you look at the highest power of x, top and bottom come in with this weird thing, and all of those problems are plausible. Continuity, nah, I wouldn't emphasize continuity too much. So 1.3, 1.4, 1.6 for sure, and 2.1, derivative as a rate of change, which is the last section. Okay, now, any other questions? Yes?
So you said formula sheet? You know what you gave us? Or no?
What you can bring to the test is the limit one.
Well, that's the only one you have.
Okay, so on Canvas, there is a set of sheets that resemble what's in the back of the book. You can print those and bring those. I'm not going to supply them for you, but you can have those. You're not allowed to edit them. You can't go write your favorite stuff on it, okay? Now, as far as this one is concerned, right here.
These boys need to jump over jump.
So let's say, I'll say this about that one. I'm going to do one of two things. So bring it with you, but I'll do one of two things, and I'm not sure what yet. I'm either going to give you a small bonus if you don't use it, okay? Or I'm going to give you a penalty if you use it. I'm not sure which way. So maybe I'll say, I don't know yet. I need to think about this a little more. Because when I handed it out, I said you can't use this on the test. I mean, that was the day I handed it out. I said that. So if I'm going to change that now, I think it's going to be one of those two. All right? I think that's, yeah. But like maybe 3 points. So like if you use it, the highest you can get on the test is a 97. Okay? If you use it. If you don't use it, then you can get 100 still. You know what I'm saying? Or I'll do it the other way where I say if you don't use it, I'm going to add 3 points. If you use it, no penalty. Let me decide on that. Yeah. But make sure you bring it. Any other questions? You can go. It's past time. But if anyone have any more questions? All right. Study hard. Sleep and eat. Sleep and eat. Let me turn off the camera.
Yeah.
Make sure you sleep and eat. Do your homework.